This is chapter 24, carbon-carbon bond forming reactions in organic synthesis. Now this is kind of a funny chapter for you guys because it does cover a lot of advanced topics that I certainly do not expect you to delve into and understand every facet of all of these reactions, but it's important for you to see them because these represent maybe the majority of the chemistry that has been developed more recently. So all the chemistry that we've talked about is all relevant and still used today. But this is some of the newer things in chemistry. So it's important for you to recognize that these reactions exist and what the products and reagents are. But I understand that the mechanisms and the understanding how these reactions work is just not something that we'll be able to cover fully. That said, let's look at what some of these are. So we're going to look at organocuprate coupling. So we've seen some organocuprate reactions before. And then we're going to do the Suzuki and the Heck. These are palladium coupling reactions. And then we will look at metathesis, which is a fun reaction. And then bonus, because I'm a polymer chemist, we're going to do ring opening metathesis. The book also puts carbene chemistry in with this chapter. We are not going to do carbene chemistry. Yeah, I mean, you should know what a carbene is just for your own knowledge, but it's not. It's just a whole different subset of chemistry that we don't really have to do. So we're skipping it. Okay, reactions with organocuprates. So we've seen some of these before. The main thing to remember is that your organic cuprate is your nucleophile. And then what's different in all these reactions is just what electrophile you provide. So we've seen the ring opening of epoxides, right, where you break this bond and then you form this new bond to one of your R groups, right? New bond to R group. We've seen the reaction with acid chlorides, where you would break that chlorine bond, right? That would be your leaving group, and you get this new bond to an R group. And this will also react with conjugated carbonyls, right? You can do 1,4 addition. Actually, organocuprates are great for this. So here you just don't really break anything. You just form this new one and you break the double bond. So I can draw it like this, break just one of the double bonds. So those are the ones that we've seen before. Now we're just going to, slight variant, our electrophile is another alkyl or aryl halide. Oh, I have it there already. Right. So now we're going to be able to do a direct coupling between one R group, which will also be alkyl or aryl, and a new R group. And this will give you some new compounds that you can make. You can totally bypass oxygen and carbonyl chemistry and just make that straight carbon-carbon linker. And that's why these reactions are so important. This is just a really powerful tool. So let's see. So we have a lot of possibilities. Generally, so like I said, it can be alkyl or aryl, right? Benzene based or aromatic based, or just a straight alkyl chain. You can combine, this is an sp3 carbon, right? Whereas this is an sp2. So this is an sp2 sp3 new carbon bond. So that works well. You can do this with a secondary carbon. You can't really do it well with tertiary carbons. They're too slow. So like this would not work well. So no. But secondary is fine. So here's a sp2 aryl to an sp3 secondary carbon there. And these work with sp2 in double bond as well, right? sp2 of an alkene works really well. The nice thing is that it keeps its stereochemistry. Oops. So if it was cis, it stays cis, and if it was trans, it stays trans. How to make organocuprates, right? So this is a reaction between a halide and an organocuprate, but you can make your organocuprate from an alkyl halide. So that's pretty easy. So you start with your alkyl or aryl halide. You react with lithium to make the organolithium species, which this would be more reactive than the cuprate. So what you want to do then is add your copper iodide. Now remember that you need either 2 equivalents of your original R group or your halide, or you can just say half an equivalence of the copper iodide. That's sort of up to you, right? But two R groups are going to go onto your copper lithium organometallic structure, and then you add your electrophile, a different R group, to get your coupling, or the same if you want. So just written out a different way, if you want to go from an alkyl halide to the CC bond formation, it's generally in three steps: lithium, copper iodide, and then your electrophile. Well, your second alkyl halide. And that's, basically the extent of how much we have to go into this. So the kinds of problems that you'll get, though, will be kind of like these. I'll do one and then post the rest in the slides. But let's just do A together, right? They're saying synthesize each of the products given the starting materials. So they're giving us 2 alkyl halides. There's a bromide and an iodide. I could do this both ways. I could turn the benzobromine into the organocuprate, or I could turn the alkyl chain into the organocuprate. There's really no difference, so I'll just draw one way. Here's my iodide, and then I will treat it with first the lithium, then the copper iodide, and I'm going to do 0.5 ec. And then I'm going to do my other halide that I don't have to do anything with. And that's it. That is how I would synthesize. Then the product to this would be right here, right? So this carbon is bonded to that carbon. And that's the new carbon-carbon bond that we're forming. So I'll post the rest of these in the notes. Okay. So palladium catalyzed coupling reactions, very similar. Instead of copper, it's palladium. The Nobel Prize in Chemistry in 2010 was awarded to 3 chemists for developing this chemistry. When they refer to cross couplings like this, they're referring to combining 2 different alkyl or aryl groups with a straight carbon-carbon bond formation. So cross because they're 2 different groups. This is Akira Suzuki, this is Negishi, and this is Heck. Suzuki is like really, really nice. He's sweet. Sidebar, I had a professor, my undergrad professor had a daughter who loved chemistry too, and she wrote a paper on Akira Suzuki for her like school project, and he invited her to his birthday party in Japan at a chemistry birthday party. So he's really sweet. And this was in 2010. Unfortunately, Heck passed away in 2015. But at least he got his Nobel Prize, so that's pretty good. Okay, so the Suzuki reaction. Another thank you to Master Organic Chemistry for helping me draw these out. It is also a coupling, and here we're going to have a aryl or alkenyl halide. So aryl is aromatic group, right? So this does work with other aromatic groups, and alkenyl is off of an alkene, right? So it's a coupling of either those kinds of groups to same thing, an aryl or alkenyl boronic acid or ester. So you need to put in this boronic group first for this reaction to go. The boronic group, it just looks like this. It's a boron with 2 oxygens. Now if it's the acid, it will look like this, and if it's an ester, then there's usually some R group. So this is a pretty famous one. It's this boronic ester. And this chemistry is so popular, used constantly, that you can buy all of these boronic esters pretty easily. You can buy it. So many Suzuki reagents. So you combine 1 halide and 1 boronic acid. You need a palladium catalyst, and you need a base, and then you just form a straight CC bond. So here is that new carbon bond that was formed between that carbon, let's see here, and use green, that carbon right there, and nothing else changes in the molecule. And what's really amazing about these reactions is they're pretty happy with other functional groups. So you can have a cyano group in there, an amine, it will still work. It's not, well, so sometimes you might have the base react on the side, but you just quench afterwards. But generally, it's very tolerant of other functional groups. Right. So here's an example, right, where they have like the cyano on the other side. It's completely untouched. The only thing that gets coupled is the halide and the boronic acid. Typically, Suzuki, like 90% of the time, it's just between two aryl groups, and that like benzene-benzene coupling is really valuable, right? Because like so many times, and just even on the last quiz, I told you guys you can't use bromobenzene as an electrophile, right? You can't have your, say, your enolate attack here, right? That will not happen. And so actually making bonds directly onto benzene is pretty tricky, and this is a great way to combine to make these benzene-benzene couplings. Okay, so how does palladium do this? This is a really quick intro, but this is kind of the stuff that organometallic chemistry and inorganic chemistry will teach you. So if you keep going into more advanced classes, you'll see this. But at this stage right now, the main thing to know is that palladium, being a transition metal, is has d orbitals, right? So instead of having that octet rule with 8 electrons, it follows an 18 electron rule. Broadly speaking, it means that palladium can hold on to a lot of groups. And when you have a group attached to a metal like this, it is called a ligand. This is triphenylphosphine. Right, so phosphine because of the phosphorus, and then there's 1, 2, 3 phenyl groups. If you have 4 of these, this is palladium tetrakis triphenylphosphine, and you'll see in its like 3D structure, right, the palladium is here at the center, orange is the phosphine, and then all of these benzene rings are crowding around. That makes the palladium, it kind of protects it in a way, but as we do this chemistry, we're gonna want to bump off these ligands, the triphenylphosphine, and put in our reagents. So I'm going to walk you through the catalytic cycle, but again, this is just a brief intro. A lot of the concepts around these are hard for me to explain without going into organometallic chemistry and like explaining metals in depth. But you start with your palladium with all of his ligands happily around him. Oxidative addition is when your first compound, your halide, adds to the palladium and you boot off 2 ligands. So now palladium is holding the benzene ring on one side and the halide on the other side. Then your second benzene ring comes on. Now, so depending on, so if this is a Suzuki, this would be, right, the boronic. But there are quite a few other cross-coupling reactions that use different groups. But we're just looking at the Suzuki for now. So it also gets added to the palladium catalyst. The palladium catalyst gets rid of, the halide and whatever group was on there that comes off as junk. And then the palladium is holding both your benzene rings. And it's a sort of matchmaker. It then combines them together in what is called the reductive elimination. Here's a pretty cute little, like, this is called a ball model, right? So this is palladium here, all sandwiched in the middle. This is hydrogen. This is a benzene ring. There's fluorine on the ends in this case, right? And here's basically palladium holding on to one benzene ring and then holding on to the boronic acid group of the other benzene ring before doing this step. So here, this is kind of what this is right here. And so you can see how the palladium is just kind of sandwiched there in the middle, and he's just bringing these 2 groups together to form that new carbon-carbon bond. So this is vastly different from the chemistry that we've seen before. So you do not have to know, this mechanism. But while we're covering, it is so super useful. So there are thousands of examples of palladium cross-coupling reactions. the ligands you use on the palladium will change, the base that you use will change. It's not quite as easy as just mixing them all together, but it allows you to do some amazing things where, like, so this drug, right, has 2 aryl groups and all of this functionality, right? There's carboxylic acid and amine, just like a heterocycle. And it's a lot easier to say, build this piece and then like build this piece. I bet you guys could even build this piece on already and then do that CC bond at the end and done, right? It's especially useful if maybe you want to make this with the other stereocenter. Maybe you want to make it with, I don't know, a longer chain and, I don't know, maybe a chlorine over here. And you want to test a bunch of these, right? It's a lot easier to make each part separately, make your little modifications, and then combine them together than have to make these modifications on like the big structure every time. So it's used widely in drug synthesis. I had to show you this example. This is Quebecol, and I went to grad school in Quebec. It's a great place, highly recommend to visit once we're allowed to travel again. But basically the researchers who made this, it's a derivative of the sugar in the maple sap. And so when they synthesized it, they called it Quebecol, even though I guess they're from Rhode Island. So let's see. So they took their aryl halide and they turned it into the boronic acid. And then on this side, they had an alkene with 2 halides, and they did a double Suzuki, right? So they combined this carbon and this carbon twice, basically, here, right? And I mean, I'm surprised, 85% yield. That's really good for a double Suzuki. And you can see this is like a slightly different ligand that they used. Palladium starting material and then a slightly different ligand. And you can, endlessly tune all of these little things. And they made this sap sugar through this double Suzuki. My last example is from my current lab right now. So this reaction, this is a Suzuki coupling between not a benzene ring, but a thiophene ring. So it's still an aryl halide. The aldehyde is not affected at all. And then we react it with a double boronic acid on benzene ring. So we're putting in 2 of the thiophene units on either side of the benzene ring. And this was done by undergraduates in this very class, and it is a reaction that, it's a little bit tricky because you do want to keep it air-free. The palladium does not really like the oxygen, and if you don't degas your reaction, it will just, instead of your compounds coming in onto the palladium, oxygen will come in and boot off the ligands, and you just get black, useless metal. So you do have to be careful when you're doing these reactions, but they're totally doable by undergrads, and that's what we're doing in our lab. So we've made this compound via the Suzuki reaction. Okay, the Heck reaction. The Heck reaction is very similar. You have your aryl halide, but now you are coupling it with a terminal alkene. It works best with the terminal alkene. And put this in. And so you couple straight to that. So it's another sp2 to sp2 right? And this is that new carbon-carbon bond that forms. So yeah, between two sp2 hybridized carbons. I don't think, so the Heck reaction is pretty stereoselective for this, this end of the alkene, but not always. And that really depends on the conditions. Again, this is more advanced than we're really going to go into. But basically, at one point, the palladium is holding the alkene through via that double bond. And it can sort of choose to pair these up in either way. And that will give you a mixture of products. You can totally control this, but it makes the Heck reaction not as clean as a lot of other cross-coupling reactions. Also, I want to highlight, it's not really a dumb thing I did in grad school, but I was so clever, I thought I would make this compound, right? So it's got a terminal alkene on one side and a boronic acid on the first end. And I figured, well, that's great. I could do a selective Heck and then Suzuki, right? So I would do Heck here to form this double bond. And then I would switch conditions and I would do a Suzuki and get that single back carbon-carbon coupling, and I would get this great compound. So I think maybe a better chemist could figure this out. It's true that you use slightly different catalysts and conditions for the Heck and the Suzuki, but I gotta tell you, it still gave me a huge mess. So they're not completely separate, reactions. So palladium, even though you'll see different conditions that will favor one over the other, you can still get a mixture of reactions if you try to use the Heck and the Suzuki in the same pot. Okay, here are some practice problems from the book. Here's a Heck. Here is a Suzuki. And it's another Suzuki. So try these out. This is the extent of what I would expect you to be able to do. Basically just recognize that we're going to do a cross-coupling reaction and draw me the product. That's it. Olefin metathesis. Olefin also equals alkene, right? This is another Nobel Prize awarding reaction, and it has some really neat applications. It was discovered by Chauvin, so Chauvin learned how to do the reaction, and then Grubbs and Schrock really made the catalysts. And I'll show you why that was worth the Nobel Prize. Again, right, the catalysts really determine how the chemistry, how these reactions will go. And so that's what an organometallic chemist does. He makes these catalysts. So this was the 2005 Nobel Prize in Chemistry. And it's basically a coupling of two terminal alkenes. This is when it's just two, it's called olefin metathesis. And it's not stereoselective, though. You break up, oops, I can't write and talk. So you break each of these double bonds and form a new double bond. Technically, this reaction is reversible, very reversible, but one of the compounds that you produce is, this is, right, CH2, CH2, this is ethene gas. And if you let that bubble out of the reaction, then the reaction keeps driving forward, Le Chatelier's principle, right? And these can actually be very high yielding reactions. If you are doing this intramolecularly, it's called a ring closing metathesis. And the same thing, you have to have two terminal alkenes. And what's nice about this one, it works well with lots of ring sizes. So in a lot of the other intramolecular reactions, we often just stopped at, we said, 5 or 6 was really going to be the most likely products, and making 8 or 7 membered rings was just not as likely, because you would, the two groups would never really see each other. With the catalyst, you can kind of get around that, because the catalyst will like find one group, one terminal alkene, hold on to it, and then you can have it float around for a while until it finds the other side, and it'll still work. So these do work. You have to do them at different dilutions, right? So you want to do low concentrations, so that you don't accidentally, right, you don't want to accidentally couple to another alkene, right? You want just those two to find each other. So you do these in really dilute, low concentrations. Okay, so what do these catalysts look like? They all have a ruthenium core. These reactions do work with other metals, but Grubbs, who won the Nobel Prize for this, discovered the ruthenium cores, and they come in multi-generations. So yes, the first generation came first, but then also, as we're looking at like second and third generation Grubbs catalysts, they're also being tailored for specific roles, right? So the third generation Grubbs catalyst is really good for polymerization. It's a fast initiator, which you may not want sometimes. So, it's not that the third is definitely better for polymerization. The second is definitely better than the first, because this one is more air stable. So yeah, no, they do get better as they go. They were making improvements. Yeah, so as they made them more air stable, they were easier to handle. Because otherwise, you still have to keep these in glove boxes, but these are pretty expensive to make. This one, I think half a gram is $300, which is actually not that much, considering how complex this is. But it goes to show like how many people use these catalysts, that you can buy these wholesale, and they're not actually that expensive. But there's still lots of publications going on. Researchers are still looking at changing any of these groups, right? Changing these ligands on the ruthenium catalyst changes its reactivity and can give you different results. So there's lots of research still going into this, right? And this is what you would learn in inorganic chemistry. Okay, ring opening metathesis polymerization. It's my favorite little thing. So this is ROMP, and let me fill this in. So what this reaction is you take a double bond that is in a ring. You bring your metal, your Grubbs catalyst, and it will form this box, right? These new bonds here, and then it will reform the new double bonds. So this one will go here, yeah, and this one like this. So then you form, right, new double bond to your R group here, and a new double bond here. And importantly, you open the loop, basically. But because it's a loop, it's still attached. And now when I come in with, say, another reagent, right, that double bond on the metal keeps reacting, and this keeps polymerizing. Now this works really well if you start with a alkene that is in a ring, but in a strained ring. So this is norborine, and so you can see that this is just two different projections, right? So as this double bond breaks, you still have this five-membered, so 1, 2, 3, 4, 5, right? This is 1, 2, 3, 4, 5, and then, you know, these bonds are here, right? So you still form, you have that strain is released when you do the ring opening metathesis, but you still have that linker. So this is the loop, like over here, right? And so this is the polymer that you get. And you'll notice that the polymer still has double bonds in it, though, right? And this, so with especially the third generation Grubbs catalyst, this goes really fast, and you get high molecular weight polymers, maybe too high molecular weight. So I found this cool example on YouTube where they're opening up this 8-membered ring. Still not a lot of strain, but still there's some. So it will open this up, and you'll get this long. So this is still 8 here. Right, there's 8 carbons in that repeating unit from that 8-membered ring. But basically what they do, they add this, they added this chain transfer agent. So this 8-membered ring, because it's a ring, will react faster first. You'll get a huge polymer with all of these rings linked together. But then because these double bonds will still be there in the polymer, some of this chain transfer agent can come in and react, and that will break up the polymer, right? Every time one of these reacts, it will create an end to the polymer. So you would maybe have, 95% of one and 5% of the other, depending on how you want your polymer to look. So let's see if we can, oh, shoot. I want to show this to you. Okay, so you see they're adding it with the needle, right? And as soon as they add it, you'll see some like chunks starting to form in the reaction. But the whole reaction flask is polymerizing. So as you are making this viscous and viscous polymer, see, look, it's been a few seconds and it's basically solid, right? So now you've made your really thick gel-like polymer in the flask, but you had that chain transfer agent still present. They're going to explain it, right? So even though everything is now really like slow-mo, like gooey mess in there, the catalyst is still working, and the reason you had that chain transfer agent in the very beginning is so that it's nicely mixed in. And as the catalyst reacts, you'll see that it'll start to break up the polymer. And I just think how amazing it is that these reactions are so effective and so efficient that you can make these polymers. I mean, it's making millions of carbon-carbon bonds in seconds. And there it goes again. So now there's still polymer in there, but now because it's been broken up into smaller pieces, it's starting to re-dissolve and be more fluid. Right, so that was a cool video, I think, of some of these polymerizations in action. And here is some practice for you. So again, this is kind of the level of problem that you'll have to you'll ever see on an exam. It's not a lot of theory. It's just sort of understanding what happens in a Grubbs in a cross-coupling reaction. So for example, if we're going to do A, it's basically we're going to couple two terminal alkenes. So we just assume there's two of these, right? And so I'll draw 1/2 in blue maybe. And then there'll be a new double bond formed, and then the other half will be pink. Sorry, 1, 2. Oh, geez. 1, 2, 3, 4. 1, 2, 3, 4, and right, like that. Right, so count your carbons, right? But basically 1, 2, 3, 4, 5. So this is 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. Right, so 3 is where the methyl group goes on both sides, and you form this new double bond. All right, there you go. So I'm gonna post these answers in the slides, and that's it for carbon-carbon bond formation.